I know this is about buildings, basically. But we all know that we cannot go ahead without thinking about vegetation, without thinking solutions about the vegetation. And so today the talk is a bit about things we have to consider when we talk about vegetation. Because I saw a lot of the posters downstairs, and there is, of course, a lot of physics involved. And the physics of a building, this is something we can rely on because we know the materials, where sometimes we don't. I saw a poster about phase change materials, so we know what's going on or what is proposed to be going on. But this is all in a white box, more or less, because this is material science, and there is no much choice to how to behave. But when we use vegetation in different aspects of architecture, we're having to deal with a living organism. So it's not a fixed thing. It's, of course, it doesn't talk to us. So it's somewhere between what we consider a living thing and a material thing. But it has its own requirements. It has its own way of acting. It has its own way of doing things. And this is often neglected. So this talk is maybe a bit out of the box about thermal things of buildings. But I think this is the intention of a keynote, to be a bit out of the box so that you get to think about something. And I hope it will be useful. So I will also have some equations here, but the meaning of the equation is not too much to understand the equation in total, but it's to see what goes into the equation. It's like cooking. If I want to introduce a new kind of crepe, it doesn't really matter if it's 100 or 200 grams of sugar, but it's important to know that sugar is still an ingredient of that recipe. And this is why I show the equations, just to show what goes in it and what are the driving parameters. So you all know these pictures. I have just taken some of them. There are thousands of them. So the integration of vegetation in the urban context, in the architectural context, in the urban context, so that's the thing that is really up to date. So that's a hot thing, I would call that. Everyone needs to do that. It doesn't matter if it's a rooftop greening, if it's a facade greening, if it's trees in between the buildings. But still, we're always thinking about vegetation as to be placed as an item, like a rooftop insulation. But that's not really true, because this is a very depressing picture, I know, but it's almost November, so we can do depressing pictures. So this is Hyde Park in July 2010. And you know, the English people are very proud of their greens. And if Hyde Park is in that condition, where there is no green anymore, you know that something went wrong. Or something in the face of climate change has progressed into a direction where the systems as we know them are not function anymore. So obvious, this grass, or I don't know if we call that grass or it's hay, will not serve as an ecosystem, will not serve as a thermal instance in the system of urban environments as it was proposed to be. So many designs, many architectural designs, many ideas of how to integrate vegetation are always assuming that vegetation will be vital, vegetation will be there, vegetation will be at the maximum of its performance. And like humans are not at the maximum of their performance most of the time, that is the same for vegetation. It naturally does not need to be as severe as that, but it's a general problem. And this is what this talk is about. There is another issue about urban vegetation that is more about trees, planting trees, setting trees, not too much about rooftop, maybe also about a bit of rooftop trees. This is wind risk. So this is a picture from an event that happens in the Ruhr area where I come from in 2014. So it was a massive thunderstorm cell, so similar to a hurricane or a tornado, which destroyed about 20 to 30% of the green infrastructure in the area of the Ruhrgebiet, Essen, Düsseldorf, and so on. So that's the other aspect. What shall we do? can we really place plants, trees, huge plants, so basically trees, everywhere? Or what should we think of? So we are not having always clear skies and light sunshine and light winds. We also have to face the events that these severe thunderstorms are increasing in their frequency of occurrence. They're increasing due to climate change and due to the enhanced amount of vapor in the atmosphere. So we have to deal with that. Will our green infrastructure stand these mechanical loads? And I will show you something, how we consider these mechanical loads and how we can work with this in the face of urban planning under the face of climate change and the imposed changes. So basically, if we sum it up, we have two risks we have in vegetation or using vegetation in urban areas. So the first point is I will give a short introduction about the state of the art about modeling trees, because there's a lot of things that have changed in the past. And then the last 2 points are about risks. The one risk, or the first risk will be the heat-water risk, which is combined. And the second risk will be the wind risk. So let's just dive into that, just to give you a small update how models work. So I'm not going to focus on a specific model. Fazia said my model is ENVIMAT, so I developed it 30 years ago. Not 30 years ago, since 30 years. So basically, I know much about ENVIMAT, but it's the same for all models. So could also in Maisonnage or in Palm or whatever model you name it, if it goes to represent vegetation as objects, so not just a layer or some physical added properties, so really representing the objects of a tree, they all work the same way. So this is general knowledge, not about just ENVIMAT. So what actually we have is, so that in the beginning, we were using simple voxel-based trees. So we were just using objects with a structure, a geometry structure, and just filled them with leaves, and then say, okay, let's go ahead with that one. But that's not really true, because a tree doesn't look like that. And especially, which is important for its performance in thermal aspects, its performance in wind aspects or evaporation. It's more better to know a tree looks more like that concerning the leaves, and it's based on a skeleton, basically twitches, branches, stems, and whoever knows what is a part of the tree. So that's basically the state of the art we're having today. So we are not working, we should not be working with trees as that simple. So we should work with more trees that really do look like trees. And one of the parameters when we talk about vegetation, you will always hear, and I would just mention that once because otherwise you will be maybe confused, is the leaf area density. So that's a very important parameter. So like you have the U value or the heat transfer value at a rooftop. For tree modeling, the LID or the leaf area density, that's the most important parameter because it defines the density of the material. So it's really just defined as the amount, the amount of leaves, so the leaf surface, per air volume. So if you have a very dense tree, you have a very high LID value. You have lots of surface for the leaves are related to an air volume. So there are different things how we can generate trees, because I just said we don't want to use trees very simple, not just bubbles, not just cylinders, not just circles. So we want to have them more precise, because this makes a big difference in the way they work. It makes a big difference in the evapotranspiration, it makes a big difference in the wind risk. And so we are basically having two possibilities, like always, to generate things. It's the same like in architecture. So the one thing is you can use generic things like algorithms. So for example, you can use what is called an L system. I'm not going to do much in that. That's an old thing from the 1970s, where it's basically a replacement grammar system where you use numbers or letters, and each letter stands for a certain aspect of the tree, just generate a branch, turn to the left, turn to the right, generate another branch, and you can, like in a fractal-based thing, replace all these things, and from a very simple rule, you can generate quite complex objects. Of course, all these trees will look like the same because they are based on the same generic algorithm. So like your buildings all look the same if they are based on the same algorithms. The other option basically is that you use LiDAR, so that's a laser scanning basically. So this technology has very much advanced in the past, and it allows you to really gather your trees that are existing in your urban environment, existing trees of course, scan them with the LiDAR system, and then reproduce the system. So you're starting with a point cloud. So this is the thing the LiDAR system generates, and then you generate the skeleton, the branches, and finally the final model of the tree, often using AI approaches. If you know it's a maple tree, you know how the basic rules are, how branches are generated, and so on. So let's go into, so that's the state of the art. So you can really have your tree models of your urban environment. It's a bit costly, but not too much anymore because any mobile phone already, here the iPhone, already has a LiDAR, a small LiDAR. You cannot use that LiDAR for measuring trees, but this is 6 years old, and it dropped several times. But the LiDAR systems are getting very cheap, and with the LiDAR systems, you can get a complex 3D meshes of your trees, buildings as well, but we're talking about trees right now, which gives you the possibility to have the tree in the model as it really is. So including its history, it has been chopped here, chopped there, dropped there. So you have the exact trees. Okay, so let's talk about heat and water risks, because we talk about urban vegetation or green as a mitigation factor for counteractions against the global change, the global climate change, and especially the impacts of heat waves in urban areas, the urban heat island, excessive heat events. And so what are the risks for a tree? Not only humans are exposed to these extreme conditions, also the vegetation is exposed to extreme conditions. And I think we all can agree that it is not a sustainable approach to plant a tree somewhere, not thinking much about the location of the tree, maybe thinking a bit about the species, but normally you buy, as a community, you buy the tree species which is cheapest at the time you need them, just putting them there and let it die. And then 5 years later, you all know the situation. Newly planted trees, 50% of them are dying in the first 5 years, and then they're going to be removed and probably never been replaced with a new tree. So I think this is not a sustainable approach. So we need to understand if we want to introduce green in a building as well as in an urban context. It doesn't really matter if you go for a rooftop or you go in the space between the buildings. You have to really consider what are the specific conditions for this tree. And they are quite specific in an urban area. We have a modified solar insulation. I will give you an example later on. We have limited soil space, very obvious in an urban space. You have roads, you have parking lots, you have other things that restrict the trees, and a tree that normally would have a large area of rooting zone will not have the possibility to do that in an urban space, and this has an impact on several aspects of the vegetation. We have limited water storage in the soil because we have urban soils. These are highly modified soils. They often contain building construction materials in an urban area. So they do not have the storage capacity of water that we normally could expect if the tree would stand in some open site or in a farmland or somewhere else. And also we have a damage of the root system. That's something that is very severe because it is not really something that is going to be reconstructed. So if you have a tree at a road and then you have a construction site at the road, and very often the roots of the trees are chopped and these roots are gone forever. They will not recover anyway. So this is the first equation. So as I said, it's just for the integrants. So what is actually the factor that drives the impact of a tree or vegetation. I just say tree, but you can take any vegetation you like, bush, climbing plant, or whatever. It's the same for every plant. So what is the impact of a tree? First of all, it's shades. Okay, that's very simple, so let's drop the shade. We also say the tree cools, but is this really true? The question, if something cools, and this is the same for architecture, and this, we are going back to the thermal aspect of this conference, if an item cools, or an item has the possibility to cool something, it has definitely to be cooler than the item it is going to be cooling. So the leaf has to be cooler than the surrounding air. If the leaf is hotter than the surrounding air, it does not cool down the air, obviously, because energy always flows into the direction of the gradient. So if the leaf temperature is higher than the surrounding air temperature, a leaf will not cool down the air, it will heat up the air. So this is the first thing many people do not expect from a tree. They say, oh, a tree is always cooling down. No, that's not true. So have a look at this tree. Just look at the colors. You see, as this tree is placed in a very heterogeneous environment, different wind speeds, different kinds of shading, different solar insolation, close to the building, far away from the building, a leaf does not have one air temperature, one leaf temperature. A tree has several leaf temperatures. So it's just the right time in years. So if you go down the street and look at a tree, you will see that there's a lot of patches of color. So there are some leaves which are already fallen down. There are other leaves which has already been red, and there are other leaves which still look green. So that's, in principle, the same thing. So if we want to cool, we have a cooling capacity. The leaf has to be cooler than the surrounding air. That's a definite thing. If it's hotter, it will increase the heat of the surrounding environment. So in going into the equation, that means so a leaf is very thin. It does not have a lot of heat storage, so it basically balances out its heat equation. So that means everything that comes in as radiation, so that's basically the shortwave radiation, so the solar radiation directly or reflected from the surrounding buildings. And on the other hand, the long-wave radiation, so the thermal radiation, that's the input part of the whole thing. That's all the tree can collect. And if the tree at least wants to stay at a certain temperature, it has to release all this energy again. So and there are only two ways an item can release energy. And the two ways are through sensible heat, through feelable heat, like a wall, or the other option, and this is something that is specific for a tree, it can, sorry, I have a mistake here. It should be latent heat. Sorry, this should be latent heat here. So it has the option to lose energy through vaporizing water. So that's the only specific thing that a tree can do. And so let's go to a little example to show you what it is about. I'm not going to talk too much about equations today. So this is an urban park in the area of Essen, so where I come from, but it could be an urban park in Paris or wherever in Marseille. So it doesn't really matter where it is. It's just an urban park, a typical size. I think I have no size in it. It's about I think 200 meters here on that side, and it's about 400 meters on that side, and it's surrounded by heavy urbanized areas. So the question is, what will be the impact of that park? So it's a very typical question in today's urban planning. So we want to introduce an urban park. What can we expect as a bell function of that park? So we have two points that will be interesting later on. So the first thing is, I just mentioned that if you talk about trees, consider that the location of a tree in an urban setting is very different to the location of a tree in an open landscape. So for example, this is a large tree which is situated here, and this is a solagram of this tree. So this solagram basically shows the days of the year. So this is January, this is June, and this is again December. And this is the hour of the day, early morning, midday, and night. And what you see here is the available radiation, the available solar radiation. Just look at the colors. So the maximum are 61% of the available radiation. And you see this tree only has a very, very limited access to solar radiation, actually, and only in the afternoon hours in the summer, and there is almost no incoming solar radiation all through the day up to 14 o'clock all day through. So this is the one thing. So if we plant a tree, make sure that you know about the setting where it is planted. Make sure that you know about the solar radiation that is available to that tree. So you cannot plant, for example, a palm tree in that location because it would simply die, because it needs a lot of solar radiation. Okay, let's have a look at the air temperature. So this is how my work normally looks like. So this is a map of the area. So this is the park area here. These are the surroundings here. And this is the air temperature during the day. So just look at the colors. So obviously the blue colors stand for cooler air temperatures, and the yellow to red colors stand for higher air temperatures. So you see the range. It's about, and the highest colors, or the highest temperatures are 28 degrees centigrade, and it goes down maybe to 23. So the range is not very large in terms of air temperature. But you see, the park is doing its job, so it's a cool area, it's cooling down the air. But what you also see here is that basically the effect of the park is limited to where the park is. So that's something we have to deal with. So many people say, okay, wrong direction. Many people say, let's use a park to cool down the urban neighborhood. Well, but that's not true, because the influence of an urban park, it doesn't matter how large it is. Think about Central Park or so. You cannot make a larger park than Central Parks, basically. It loses its effect after 200, 300, maybe 400 meters, depending on the road and the building structure, but then the effect is gone. So basically, if you want to have the cool effect of a park area, you have to go there. Do not expect that your park will cool down the surrounding environment in a radius of 100 meters, sorry, not 100 meters, in a range of 1 kilometer or so. That will not work, because there is so much energy stored in the materials of the buildings, of the roads. It will destroy immediately the small cooling effect generated by grass and trees. So that's the one thing. But I want to talk about risks. So that's the nighttime effect, so just going over there. So the thing, what I just said, when we go to this equation, the way why the park is cooling down things is because it can transfer vapor, it can transfer water, liquid water, into vapor, because this is a physical translation, so it's a liquid phase to gas phase transition, which uses a lot of energy. And this is the basic mechanism how trees are cooling down themselves and, of course, cooling down the environment. But this has impacts. It has boundary conditions if it works or not. And one of these steering parameters are water availability. Do I have enough water to make this, to cool myself down? Do I have enough solar radiation to trigger this process? What is the air temperature? What is my vitality? And what is the CO2 concentration? You see, there are really a lot of boundary conditions that basically drive this seemingly simple question: what is the latent heat flux of a plant? And in many models and in many studies, people just assume latent heat flux is always optimal. But that's not true. In the picture I just showed you, I also assumed that this latent heat flux is optimal. That means the tree is vital, the tree has enough water, the tree is not damaged, the tree has no pests, the tree is not in any way ill. But what if this is not true? So let's have a look at a longer period, a longer simulated period. Let's have a look at two sites. So this is, definitely this arrow is wrong, I don't know why. So the parking lot, sorry about that, should be here, not there. So this is the parking lot, which is covered with asphalt. So it doesn't have anything to do with the park itself, but I need that as an example for the thing I will show you in the next slide. And the other point I will going to look at is a location in the middle of the park, more or less. Sorry, the arrows have been shifted due to some reason. So that is here. So this is a point in the middle of the park, below the trees, covered with grass, and so on. So a typical park situation. So let us assume that we have a long time heat period, 10 days, 15 days. So every day is hot in summer. So this is a typical thing. So typical heat periods in the face of climate change are expected to be happening more frequent. That's the one thing. And it also be expected to be a longer lasting heat period. So this means the circulation system, the high pressure system over the Mediterranean Sea, over the Azores, these are going to, they expect that they will be much more long lasting than they are at the moment. So what happens to the surface temperature under such a heat spell of 10 days, 15 days? So for the surface temperature of the asphalt, so that's the asphalt, you see, there is an equilibrium. It's starting here, but after this is day 1, day 2, day 3, day 4, and these are the other days. And you see the surface temperature doesn't change anymore because there's an equilibrium. The heat has found its balance, and it doesn't really matter if the heat wave will go on for another 20 days. It will not get hotter. It will find its it had found its amplitude, and this amplitude stays the same basically forever. But that's only true for the artificial materials. If we look at the situation in the park, you see nothing is in equilibrium after 10 days. It's still heating up. So the day number 10 is still significantly different to the day number 9, to day number 8, to day number 7, and so on and so on. So that means everything is still changing under such a heat spell, and it will for 20 days. Day 20 in a long-lasting heat spell will be different to day number 19. So there is no thing like an equilibrium in thermal aspects in an urban park. So let's have a look at the vegetation in the same range. So what you see here, the green line, this is actually the evapotranspiration from the plant. In the first day, you see there's a lot of evapotranspiration, and the red curve, that's the heat transfer, the sensible heat transfer, so what is going to be transported as energy from the leaves. And you see during that day, or during that heat spell, water becomes rare. The tree is reducing its evaporation. And in consequence, as it's not evaporating much more, the heat is going up. So that means this tree is going to lose its cooling potential, and it will go ahead heating up the lower air. So what we actually planned as a cooling device will be a heating device later on. And if we carry on for several days, you know what the effect will be. If the leaf temperature goes ahead 40 degrees centigrade, the leaf will die. This will destroy the cell structure. Depending on the tree species, of course, there's a certain range. But in general, if the leaf temperature goes above 40 degrees centigrade, the tree will die. The leaf, not the tree itself, but the leaf will die, and the tree will shed its leaves, and then there will be no cooling anymore. So when we think about the effects of this urban park under the aspect of a heat spell, so what will be my cooling effect, my nice picture, the nice graph I just showed you, will this still be valid after a heat day, after a heat period of 10 days? Probably not, because we have seen the trees are losing their ability to cool down the air. So what will be the effects on the two-dimensional or three-dimensional urban system? So this, for example, is maybe a bit complicated map, but it's not that complicated if you just look at the figures. So what we have done here is we used a the cooling potential on the first day of a heat period and on the 8th. Yeah, and very simply, what you see here, everything that is red means that on the last day of this heat period, the park will be 1 degree centigrade warmer than on the first day. So that means all the red bubbles here, these are areas where the park has actually lost its cooling potential. And 1 degree is a lot of cooling potential. Normally a large park like Central Park has a cooling potential of 3 degrees, maybe 4 degrees centigrade. And even after 8 days, if you have lost already 1 degree of cooling potential, so this is something that really has to be considered. If you use urban spaces, urban green spaces at a mitigation factor, saying I expect my park to cool down the urban areas for 3 degrees or 4 degrees, and if you do not have any additional measures like watering, like tree monitoring, then this perspective is simply completely wrong. It will not work. It's like in a building where you think of optimal inhabitant and you design the whole building, the whole heating and the cooling and so on for this optimal inhabitant, but this optimal inhabitant will never move in and your building will not work. That's the same for trees. Yeah, and this is the end of the story then. No longer vitality, and we all know trees. So if there is one heat spell that kills it, the tree will be gone for the complete summer. Okay, let's move to the second risk I just mentioned. This is the wind risk, or the damage of trees. This is two-folded, because on the one hand, we don't want our trees to be damaged, of course. But on the other hand, it's also important for our infrastructure, because there's a lot of critical infrastructures, ambulances, fire brigades. They have to be able to move through the roads. And remembering that figure from 2014, that was not possible in Essen because the roads were covered with trees, fallen trees, damaged trees, stems falling down. So it was also not only a severe incident for the green infrastructure itself, but it was also a severe incident for the public situation at all, because police, ambulances, fire brigades were not able to pass the roads anymore. So that's something that belongs to critical infrastructure, and definitely something we have to look at. And what are the risks? What are the specific risks of trees? Why are urban trees specific risky? I mean, they are not much different to trees in a forest, but if it's it's a storm event, no person who is thinking normally is going to the forest. But in an urban area, you can't avoid to be there because you live there. So what we have there, we have the tree crown geometry, which is very important because we have to see the interactions between the buildings. Does my tree goes ahead of the highest building? So is it exposed to the wind that is above roof level? We have the in an urban area, especially the condition that we have high local wind speeds. You all know that we, through the buildings, we can generate the Venturi effect, so we channel the wind. That means that we do have an increase of wind speed due to the building constellations. And we also have, during storm events, unusual wind directions. So why is this important? Because normally trees are used to their environment. So they look, you don't see it from the outside, but if you have a tree which is constantly exposed to western winds, like in Paris, the western wind directions and the northwestern wind directions are the most common wind directions. These trees are used to that wind direction. That means they have built up internally stronger elements to protect the load that comes from westerly winds. But if we have a storm event, like a supercell or a similar or a tornado-like event, it's normally coming with a very untypical wind direction. It could be a southern wind or a northern wind in areas where you normally do not have northern winds or southern winds. So that means the trees are not prepared for that. They have not developed the mechanical infrastructure to protect themselves from this wind direction. So these unusual wind directions are really a problem because the trees are really weak on these unusual wind direction sites. And of course, temperature, humidity, and soil water. So what I just mentioned, these thermal aspects always have an impact on the tree health. That does not only belong to the evaporation, but it also belongs to the wood. So if the tree is low of water, it will change the composition of the wood, because a living wood, a green wood, so I'm not talking about wood in a building construction, but I'm talking about wood which is still in a living organism, is composed of several things, including water, and the flexibility of this wood will change if there is a water risk. If there is not enough water, the rigidity of the wood will change. It will not be flexible as before. So many trees break after a heat spell. So if this heat spell would not have been there, if the tree would not have been dried out, probably it will not break. But as said, these things are interrelated. As there is a water shortage, the flexibility of the trees, of the branches, will be reduced. And this means if this heat spell ends up with a thunderstorm, which is very often the case, we have two things at the same time. We have the thunderstorm, which is a risk for the tree itself, plus the situation that maybe there have been 10 days of low water. And that means that the flexibility of the material, of the wood material, is decreased. And this will also increase the chance that it actually breaks. Yeah, just to show you some equations. So basically, what happens if there is a tree standing in the wind, is that mechanical energy from the wind, it's floating air, it has a density, it has a velocity, that means it has a momentum, and this momentum is transferred from the air onto the tree. And this could be, oops, wow, that was loud. This would be transferred basically onto the leaves and onto the twigs. And like in a construction, this mechanical load is being added to the skeleton of the tree. So if you have a wind coming from that direction in that image, you see the tree is bending out of its neutral position. So that blue line, this would be the neutral position where the tree would stand if there is no wind or only little winds. And you see it's deforming. It's starting at the crown, it's collecting all the forces top to bottom, and if it has the possibility, it will deform itself and hopefully not break. But if this happens, these are the typical results we see. Just to give you a very simple example to tell you how complex it is. It's much more complex than you think. This is a very simple setting I have introduced. So a row of large trees, a row of smaller trees, and a row of trees, large and small, with between two buildings. And the wind is being introduced from that side. So I just take this model and let just the wind blow through the model, just to understand what are the wind conditions for the trees. They are so different. Assuming that all the trees are the same, but they are exposed to so different wind environments. So let's make a section. This is our first section here. And let's have a look at the streamlines. So they are not too much interesting. I will go ahead with here. So let's have a look at the wind speed. So red is the original wind speed. High wind speeds are red. Low wind speeds are blue. And you see the wind is coming from here. You see the very first tree in that row is completely confronted with all the wind coming in. So it has to take all the mechanical loads that comes in. The second tree is already sheltered by the first tree. So it's there, it does really there's almost no wind speed coming to that wind crown, and the same here and the same here. So there is a small gap between, so the wind has the chance to recover and go back in here. So this tree always has some more wind speed to carry on, but it's no comparison to that tree in the first row. So this is why you have the effect you often see that I just said trees are growing with their conditions. This tree will be trained. If this tree has been grown at that situation, it will be trained because it knows I am the first one in the row. I'm the poor tree which has to capture all the wind speed normally. But it will react on that. It will be stronger. It will have much more wood material phases in it. What happens then if the other trees are here and they all have been planted at the same time, which is not unusual for an urban environment. So this tree never had the necessity to protect himself for strong winds because strong winds never happens to him. He was always protected by some other tree in front of him. That's the same for the other trees. And so now something happens, you build something here or you have to remove that tree. Then the situation comes that now this tree here, tree number 2, now is in the first row. Now he is the one who gets all the wind impact, but this tree has never learned to do that. This is what we often discover in forests, for example. If for some reason you remove the outer line of trees in a forest, you can discover that often the complete forest collapses afterwards. Because the outer trees, they are the trained trees. They are the one who have been responsible for their whole life to capture the wind speeds. And they have the mechanical properties to do that. If you remove them for whatever reason, and the next row of trees is now the first row, but they have never experienced these winds. They have never grown in a way to protect themselves against these high wind speeds. They will fall down very, very quickly. And also, if we look at buildings, so these are the streamlines, you see how complex wind patterns are behind buildings. So you have all the vortexes here, the recirculations behind the buildings. So that doesn't mean we do not only have different wind speeds, we also have strange directions of wind. They're coming maybe from the top to the bottom, or they can be directed from the bottom to the top. So any of these trees have their own wind environment in which they stand. They have their own wind environment they are used to be. And you cannot interchange these trees. So this is the wind speed again as an example. And looking at the top of it, so this is a bird eye perspective of the whole thing. Again, you see the wind which is entering the trees, and you see all the red colors. These are the well-trained trees. So these are the trees who are used to stand in the wind. They know I am the one who gets all the wind, so I'm organized for that. But you see all the buildings here. So you see this tree here is always been in the neighborhood of this building. So there was no reason for that tree to be organized as a strong tree. It has never been in charge to protect itself from wind speeds. So what happens if you demolish this building here? So suddenly this tree will be in the same position like that tree. So all the wind suddenly will come directly onto a tree which is not prepared for that. So you can imagine what will be the consequence. This tree is very likely to fall down very soon. Although it's the same species like that one, but it's not trained. His history has never been a story of being exposed to wind because the building was protecting itself. So going to the final step. So yeah, I'm almost on time, over time. So this is what we do. So we're not only looking at the colors of the tree crown, but we also simulate the forces that are being transferred through the tree. And so that means basically, like here, you see this fat bird sitting on the tree. So any force that is applied to a branch, maybe it wind or maybe it a fat bird, is going to be transferred into the inner wards of the tree. And that means we have to solve all the equations. So it's basically a mechanical calculation, a bit more complex because, of course, the tree reacts on the forces. If the wind is coming, the twitches or the stems are moving themselves. So it's pretty complicated. Just to show you the examples, I know I didn't have the time for that one, but just to show you, I have a video for that. So this is a tree on the northern Frisian island, and you see how complex the movement is. So I did it in a time lapse. You see that all the elements are moving in a very specific way because the thing is that the tree, of course, has a lot of weight. So if you move a part of the tree with the wind and it weighs 100 kilograms, for example, and you move it with the wind, it will not stop at the end because it has a motion, and it will just break because you put some high amount of wood into motion. And this is something you also need to model. So if you want to model wind risk, you cannot just say, okay, this is the wind speed, this is the tree, what is the risk? No, you really have to understand the event, the wind event. How is the wind progressing? Has it a peak, or is it slowly increasing, staying at an amount and then defalling? So that makes a huge difference. Yeah, so that's very, very specific. So this is how the software looks like if you want to analyze things. And this is something, for example, you see here. So we do have a wind impact, and this would be the stationary solution. So this would be the twitching or the movement of the tree. But once at the beginning, when the wind impact comes, it will move far away from its neutral position. So it will change its position by 7 centimeters, while the neutral thing will be about 5 centimeters. Yes, so that's just some figures on how the software works. What we do is we take every tree in the model and investigate it and put all the wind directions and calculate the complete wind rows over all the different directions, over all the wind speeds, and basically testing all the trees. How do they bend? Is there a critical moment? Is there a critical load on the wood? How are the chances that something breaks? And if something breaks, what is it? Is it just a small twig and no one cares? Or is it a branch with 500 kilograms dropping down onto my car parking below the tree? Yeah, and we can do this thing in the model. So we did that for Essen to understand this summer storm event. Just show you a few pictures how it looks like. So this is the original configurations. These are the platanus trees standing there, and this is the model representation. And you see it's a lot of different, it's much more detailed than the bubbles that have been there before. Yeah. Yeah, so that brings me to the last slide. So trees are exposed to risks, and if we want to have them sustainably working in our designs, it doesn't matter if it's on a rooftop, it is attached to a facade like on the Bosco Verticale, or is it a part of an urban park, we have to make this sure that we understand that trees are living organisms. They are having a cooling potential, definitely, but if we have no water available, we have dry soils, we have dry spells, they will lose their cooling potential. They could be even worse. They could die, or they could heat up the air because the leaf, a dry leaf, is very, very hot, basically. And it takes damage. We can have dry soils, dry woods, high wind speeds or peaks of wind speed can destroy this tree structure. We have these unusual wind directions where the tree has not been trained for in an urban environment. Often what we see when people are not coming from landscape architecture, or they are not considering all these aspects, is they put in the wrong species in the wrong place. So you really have to consider which tree will fit in which location, considering solar input, considering wind load, considering almost everything to make this a sustainable design. Yeah, and of course, numerical simulations allows you a general risk assessment, but it's a risk assessment. So I cannot say, oh, this tree will fall. It's like I can do a risk assessment for cancer. So there are people drinking 1 bottle of vodka each day and are still healthy at the age of 90. So this is the same here. So it's just a probability that we calculate. There's a high probability for this tree to break. But we cannot, of course, exactly say which branch will break, because there are so many other things like pests, damages, and so on. So this maybe is a big difference to maybe calculation of building statics, where we exactly want to know which figure or which load is on each balcony. That doesn't work for trees. Yeah, so this is basically my last slide. So, merci beaucoup. Overrun a bit, sorry about that.
Thank you very much for this very interesting presentation. I have learned a lot about the new developments in ENVIMET. So we have time for a few questions. Yes.
Okay, at first, thank you for your talk. It was very interesting. I enjoyed. Complex problems, so I have many questions. I will maybe just limit to some questions. At first, you didn't speak about species of trees. For example, to generate the skeleton of trees, do you use this concept of plant architecture developed by Haldeman and Elle years ago? First question. Second question, evaporation. Yes, I agree. Evaporation is mandatory in the temperature of leaves. What you call vitality, indeed, could be probably obtained by the water potential in the soil. Probably the soil potential decrease, which is another very complex system. So do you account for water potential in the soil to try to predict how this temperature will evolve over days? And maybe last question about wind behavior. Sometimes in forests, for example, it's not the first layer of trees, the first row of trees, but the second one that will break because of turbulence. For example, trees are very sensitive to the torsion of trunk. For example, von Karman alley is very dangerous for trees. I've seen some von Karman alleys after building in your presentation. So have you seen something like this about these trees subjected to movement over time of wind, not necessarily a huge intensity, but a variation over time that will have a resonance of the structure and will break down? So I will stop here. Thank you.
Okay, I'm killing microphones today. Yeah, so the first thing is, yes, we are using these algorithmic trees like Lindenmayer or so when we do not have better information, because it's better to have at least the species, a maple or ahorn or whatever, rather than just a bubble of trees. But we are really hoping, and we see that it's happening, that the cities are generating a more intense tree cadastre where they have LiDAR data, and you really do have the tree as it looks like, because if you do it on an algorithm way, they all look the same. And if you go outside and say, oh, this tree does not look like in my model. But of course, if you do planning, the trees are not existing yet. So if you plan to make a row of trees which are not there today, you have to work with algorithm trees because you don't know what actually happens. So we have, of course, some rules how they will grow depending on light access and which direction they will move, but it's really hard to say. Depending on the soil question, yes, urban soils are very hard. So we also have a soil model. So we have a root, like you see in the upper sphere, we also have a root model, an estimate how the roots are distributed, and we have an estimate of the soil capacity, the Darcy equation in the soil, and the water capacity of the soil. But it's really hard because you never know which soil you have in an urban area, and you also never know where the roots of the trees actually are, unless you make a radar, a root radar or something like that. And yeah, for the turbulence, yes. So at the moment, what I showed you are Rand's equations. For the impact of a time series of events, as I said, because there is hundreds of kilograms moving, and it's very important to know where it is when the next impact comes. So it could be, if they are far away, and the next impact comes into the next direction, they will get another movement in that direction. So probably using the LES equations for the wind speed is probably the better way. But actually, this tree model does not depend on the microclimate model. So this is completely isolated. So if I do have a good series of wind events measured, or from LES, or from wind tunnels, or whatever, we can feed it into that tree and use it, because it doesn't need to be ENVIMET or something like that.
I have a question for you. No, it works. Thank you very much for your nice topic.
Thank you.
I am not familiar with this topic, but I have two questions. One is related to your model. About the motion of the trees, and at what scale are you describing this phenomenon? At a leaf scale or branch scale, or what are? This is my first question, and my second question is about how are you validating your model, global model, in the sense because many people are now dealing with a lot of measurements in the urban cities, many huge number of points and time series. So what is the link with this work, experimental work? Okay, thank you.
Yeah, so we are working on micro scale, and for the tree it's really micro scale. So the tree segments are about 20 centimeters to 10 centimeters large, so that each tree is represented by 100,000 of elements. So this is very high resolution. This is why we only pick one tree, analyze it, and take another tree. So we cannot do it, or we could do this, but it takes a long time. So this is really on the meter level. And concerning the validation, this has to be a two-step answer, because one thing, the first part I show you, to the thermal comfort thing, the thermal aspects thing. So ENVIMET is now 30 years old, and I think there are about 3,000 papers on Google Scholar about validating. So we are not validating our software because simply we don't have time for that. And we also believe that it is more fair if someone validates the software who has not access to the source code, because if you are the programmer, you can validate everything. So there are a lot of papers all over the world who have validated measurements, thermal aspects, water aspects, pollutant aspects, and so on and so on. But for the trees, this is new field. So I think this will take another 10 years or so that we have enough material also from the measurement side and also from the input side. So the LiDARs are just developing. So this is pretty new. So there is no validation yet. So it's just a theoretically thinking, how will it bend and what will happen?
More questions?
Donc, my question concerns the global rayonnement. In diaporama 15, I think you have taken into account for the direct rayonnement. My connaissance is the rayonnement who attain a point at the Earth is the sum of the reflected rayonnement, diffuse rayonnement, and the direct rayonnement.
Yeah, I have not been talking about the microclimate model today, but basically it's the tree are sitting in the environment. And this environment has a radiative scheme, so that it is based on ray tracing, and it includes reflective radiation from the buildings, from the sky, and also the radiation passing through the tree is a very complex thing because it's scattered from direct radiation to diffuse radiation, and it goes lower into the tree. But that's all included in the environment model itself. So I'm just using that as a.
And my second question is about the pressure for the latent heat transfer. Mm-hmm. But is the pressure is taken into to account for this model?
You mean the air pressure?
The pressure. Pressure.
Oh, the threshold. Oh, yeah. Yeah, that's really interesting because there is a lot of research missing actually at these parts. So how do trees react on missing water? So it seems that there are two kinds of species. The one species is a group of species. The one species is wasting all the water. If it's available, they're just throwing it out. And the other group of species are more conservative, so they try to go ahead with the water they have. There, you can put it in as a threshold, but at the moment we are lacking of data for that. It's easy to implement, but we're missing data, simply.
Thank you.
Because you cannot eat trees. You know, there's a lot of information about crops and so on, but for trees.
Okay.
Hi. So my question mainly concerns the wind risk that you have previously shown. So. Okay, so I would like to ask regarding the equation that you have shown for the transfer of the kinetic energy. There's a drag coefficient in this equation. Does this coefficient that you consider takes also into account the bending of the tree? Okay.
Yeah, so it takes into account the movement of the branch itself, which may be moving out of the wind direction. So Elysian, so this is solved when we're trying to get the equilibrium of the momentum so that the branch is moving if it can, and also that the leaves are flattering or moving away from the direction, yeah.
Okay.
In your first slide, you presented three different cases of the tree, three extreme cases, and in the middle you have used the simulated case. How do you characterize the tree in this case? There is a mathematical characterization, or maybe there are some mathematical characterizations of the tree, like fractal dimensions and things like this.
Yeah, you can do both. So you can basically draw the tree. So if you have a tree, you know, this is my tree and I want to know more about it, you can actually draw it. But you can also use the Lindenmayer system, for example, which is a kind of fractal system, which is a very strong mathematical representation of the tree geometry. But you can also use the LiDAR data, which is not mathematical at all. So it's just a structural information. And you, of course, have to add all the species information to that. So you have to say, okay, this is an oak tree, and this is how the oak tree looks like. But you still have to go into the database and find all the biological properties that an oak tree has. So you have to do both, actually. But normally you cannot do that because in an area here for the university campus, for example, you have probably 2,000 trees or so. So if you go into an urban environment, for some of the trees, you really have to make simple assumptions.
I think there is one question over there.
Okay, thank you for your presentation and very interesting work, which I think is not, it's a very complex, such because it involves different submodels and different the modeling or simulation have different complexity in, for example, different parameters involved, affected by different parameters, which and all the parameters have a model apart. So I would like to know just for in slide 13 the thermal model. You give in fact the general or global equation, but I would like to see the detailed equation, especially for sensible heat transfer, heat flux, and latent.
Mm-hmm. Yeah, sure.
Do you use earlier works or in the level of the leaf, especially?
Yeah, definitely. So, as I said, it's 30 years now. And if you go to the website, env-met.info, so there are all the papers linked. And for example, for the vegetation model, that actually comes from Météo France. So we have developed that together with the INRA in Avignon, with quai. So this is basically a crop model that has been more extended to trees, including photosynthesis, CO2 fixation, and so on, to get the stomata response, and from the stomata response get the latent heat flux. Yeah, but as you said, I don't know how many pages this are already on the web. So every model is described in, 50 pages, papers, and so on.
Because I think that the question is very complicated.
Yeah, sure. Yeah.
Science is depend of the temperature and there is dynamic simulation of. Okay.
Yeah, it uses these 25 function. Yeah. So
yes.
It's the best we could get. So if there are if there would be new stuff available, it would be easy to replace it. But the AGS model from Calvé and from Jacobs, it seems to be the best model available for the scale we're using at the moment.
Second question, you consider as assumption that there is no storage, QS equal 0. Yeah. Why, in fact?
Because it's true for most of the European trees. For a tropical tree with leaves like that, for example, it may be different. Yeah.
Is the leaf temperature change or no?
Yeah, it's a steady state, so there is nothing. I mean, if you look at a tree, at a leaf, so basically it's thin, so there is no storage capacity. So it's not really like a brick who has till 2 hours after the sun is still warm, but it's not true for the leaf. So it's more or less always in equilibrium with the energy flux.
Yes, okay.
Thank you. But if you have a succulent or so in a tropics or so, probably that's not true.
Thank you.
Yeah, I think we can. Thank you very much.